Thank you so much for the introduction. Really happy to be invited here again. Last year was a lot of fun with my coworker Sal. Yeah, so today hopefully I can provide you with sort of a glimpse into what we're up to at Myovision and sort of how the technology world in general is sort of driving the innovation in this space. So just a little bit of background about myself. So I'm a product manager at Myovision. I manage our traffic analytics and optimization products. So anything that pretty much has to do with data and how do we take all this massive amount of data that's being produced, how do we really turn that into impact for our users and customers in this industry. So bit of a background about Myovision. You might have heard about Myovision, you might have not, but the company was founded around 15 years ago. Sorry, are we having, can anyone hear me? Can everyone hear me? Seems like some people are having...
I can hear you.
I can hear you.
Okay. Okay, sure, great. Okay, so a bit of background about Myovision. It was founded around 15 years ago. And started in the space of traffic counts. So I'll get into the details a little bit more in terms of the products that we have available. But yeah, that's where it started. Sort of automating the process of traffic data collection is where everything started off with our founder Curtis McBride. And we are based in Kitchener-Waterloo. We have around 200 employees. We also have a office in Germany. Some facts just to provide you some facts. There's over 8 million hours of video that's been processed over the past 15 years. We're in almost 50 states in the US mainly, 66 countries, and we've counted over 7 billion vehicles to this point, and 770 million bicycles and pedestrians. So there's actually Myovision owns almost 50% of the North American market in terms of traffic count. So that's sort of where everything started, and it's been a pretty successful in this space. So one of the products that that everything started off with Myovision with was traffic counts again. So you might have heard of the Scout device. This is a device over here. This is basically a temporary sort of device that can be wrapped around a pole at an intersection. The pole can be extended up to 21 feet, and it captures video, and then there's a sort of an end-to-end solution, right? So you capture the video, and then you go back into the office, the video gets uploaded to a system, it gets counted, and then you have a web portal available where you can access all of that data with the information and with the videos and everything. So sort of an end-to-end solution to automate the process of traffic counts. So again, like there's a massive amount of data that's being collected using this device. Over half of the intersections in North America have been counted at least once by a Myovision Scout unit. So this is some of the perks of having videos all over the world. This is a video that a monkey in Singapore was actually blocking the camera. So we get to have these perks a little bit as well. So around 5 years ago, we started to enter the more permanent side of the solution. So the Scout device that I talked about is more of a temporary solution. You can wrap it to a pole and you collect your data and you just take it away and you move on to the next one. Around 5 years ago, we entered the permanent space where we wanted to provide more permanent solutions. So we started off with the Myovision Smart Link that you can see on the left there. That is a device that sort of connects into the traffic cabinet at a corner of an intersection. So probably you've seen this, but if you're driving through a signalized intersection, at one of the corners of the intersection, you can actually see like a fridge-shaped cabinet. That's where the brain of the intersection exists. In a lot of cases, some people might not know this, but a lot of the intersections in North America, they operate in an isolated manner, right? It means that it's controlled locally at the intersection, and there is no connectivity to any central server or a central system. So what the Myovision Smart Link does is that immediately by connecting the traffic controller to this device, it provides connectivity to the cabinet, provides monitoring capabilities to the cabinet. So if something's happening in the cabinet, the power is off, a brownout, any type of issue, there's a lot of things that it captures at the cabinet. It monitors that, right? So immediately makes an isolated intersection or an isolated cabinet into a connected cabinet, where all of the data that's actually coming through the controller is also captured through this device. So it's polling the controller 10 times per second. It's capturing all the high resolution data that's coming from the traffic controller. Another system that we have is sort of the Myovision Smart Sense and the Smart View that they go together. This is again a permanent solution. This goes into the cabinet. The box goes into the cabinet. The camera goes onto the side of the intersection, and it's installed on a pole. And basically, what this does is that it's sort of the eyes of the intersection, right? There's a very powerful NVIDIA GPU in the SmartSense box, and it's doing what's called processing on the edge, which means that it's capturing 4K video at the intersection on the edge, and it's processing the video, and by running the computer vision algorithm, it's detecting vehicles and all sorts of different modes of traffic and classifying them and tracking them and sending back the data. Because it's processing on the edge, it means that the video is not sent to the cloud or anything. It's done on the edge, and only the data really goes back to the cloud. I think there's important, like I said, there's always the fancy stuff and the fancy technology that's available, but there's some realities to this world as well too. So it's not all sort of perfect products. It's products that need to integrate with a very old infrastructure, and this is the part that usually you don't see a lot in publications or presentations. Like, this is the part that's usually neglected, because we always assume that so perfect data is available and it's great and it's coming through, but that's not really the reality. The reality is this. So when you open up a traffic cabinet, this is what you see. Very old infrastructure, in a lot of cases, it's not documented well, hard to understand what's going on, and you need to integrate with whatever technology that you create. You need to be able to integrate with whatever's available here. You can't just rip up everything out and say, okay, I'm going to just start everything from the beginning. That is going to be extremely costly. The agencies have budget constraints, so it's not like they can just spend millions of dollars on renewing everything. That was sort of the approach of the IBMs of the world in terms of smart city, is that like we go in and sort of rip everything out and we build from the start. Some cities have adopted that approach, but due to budget constraints mainly, it's not a very sustainable model, and you sort of need to make incremental changes, incremental improvements to the system by integrating to the old legacy technology. So hopefully at some time when COVID is over, you can come over to our office for a tour, and we actually have a very large lab that we have all sorts of different types of cabinets and controllers and everything, to be able to sort of test our different types of technology and make sure that we're integrating into that. So about some of the exciting parts that we're working on. One is sort of the traffic AI. This goes back to the SmartSense device that I showed. So again, when I was saying like if this is processing on the edge, this is what's happening in real time, right? So what we're doing is that we've trained based on millions and millions of historical examples of what a vehicle and pedestrian and cyclist look like in real world conditions. We're training the AI to be able to detect those, and then we're definitely adding a lot of newer methods on top of that. So as you could see, previously the computer vision technology is known as a technology that that doesn't work well in adverse weather conditions or things like that. That's old news, to be honest. Like you can train the algorithm on all sorts of different types of situations. It's just a matter of having sufficient number of samples in order to really train them on that, right? So if you're just going to be training vehicle detection or pedestrian detection in perfect weather conditions, of course your methods are going to be bound to that. But if you're getting a really good sample of different types of situations, it's able to differentiate. And then the hardware goes into play as well too, right? So it's not just the camera; it's a camera with specific types of features where it sort of repels droplets and water droplets and that sort of thing. So the hardware really comes into play as well, and a combination of these will really allow the system to work properly in all different types of weather conditions. So the video part is really the interesting part in my opinion. Really opens up a lot of opportunity in the space. One of the basic applications of video detection is just actuation, right? So you might have heard of loop detectors that are in the ground at an intersection, and they provide actuation to an intersection. So basic applications of the SmartSense device is that it provides that level of detection and actuation. So you can draw zones. The zones are all virtual, so you don't need to cut the pavement in order to be able to do that. Even if there's construction, you sort of need to move around zones, it's fairly easy to do that because everything's virtual. And that's sort of just the basic sort of application of video. You can imagine video provides a lot more than just typical or legacy type of detection, right? Like the loop detector would only identify the presence of a vehicle, but with video detection, you can go way beyond that, right? You can detect pedestrians, tracking cyclists, classifying different types of vehicles. So there's really a lot going on, and the applications are really boundless. You can see here that this is downtown intersection in Toronto. A massive number of pedestrians that are passing through. Sometimes it's even hard for the human eye to be able to really count the number of pedestrian cases, but the system does an amazing job of doing that. Some interesting insights. So last year, with the Raptor Parade, we're installed in a number of intersections in downtown Toronto, and it's expanding. These are some of the stats we got from the cameras there. As you can see, there's a significant number of pedestrians that pass through intersections in the downtown area. Of course, this is pre-COVID situation. Around 46,000 pedestrians a day. It's actually more than the number of vehicles there, which is interesting. And the top one is sort of a typical day, and the bottom one is sort of showing what we captured during the Raptors Parade. There were a lot of people passing by. As you can see, like the vehicles went down to zero and then sort of picked up again as the parade was going on, and there was a significant number of pedestrians that were counted in this case. So I just wanted to provide you sort of a snapshot of what this data looks like and how data being collected on a 24/7 duration can sort of provide more into what's going on. There's another sort of view based on the data that we have. So this is a combination of the installations. This is data based on the combination of installations that we have in Ontario. As you could see, there's during when the lockdown started, there was a pretty significant drop in the number of vehicles, maybe up to around a 60% reduction in the number of in the total volume of vehicles throughout the day, and then it sort of started to increase, but we're still at around 20% less than normal number of vehicles. Something's interesting is that the bicycles versus baseline, of course, this is weather is definitely an impact here, but has an impact. But you can see that there was a pretty significant increase in the bicycle usage after the lockdown. Pedestrians versus baseline. Pedestrians dropped significantly as well too. This can be mainly attributed to the large number of intersections that we have in downtown Toronto area. So there were a large number of pedestrians there that were no longer there. So it's very likely that the large drop in that would be attributed to the downtown Toronto area. But anyways, like this is just one of the most like basic type of data that can be captured through this system. So I'm going to focus more now on sort of a data piece and AT-SPMs, if you've heard of them, sort of a new way of being able to manage traffic signals and signal lightings and timings. So one of the issues with signal timings, if you look at research, like if you search for traffic signal optimization methods, there's thousands of papers out there that talk about all sorts of different types of methods to be able to improve signal timings. But the issue is that the reality of current signal timing practices is that 95% of the intersections out there are either actuated, coordinated, or fixed time, and they're timed at best on a 3 to 5 year duration. So regardless of all of these different types of methods that have been created, the reality out there is very different. And the method that's currently used for signal timing is a spot instance in time, right? So you sort of take a device like Scout, for example, you collect a couple of hours here and there during the AM peak and PM peak. Take that data, you pump it into a software like Synchro, produces some signal timings, and then you put it in the field and you just leave it there for the next 3 to 5 years. We've seen 10, 15, even more. And there's a lot of issues with this, right? It's like you're just collecting like 2 hours in the AM, 2 hours in the PM on a random day. Is this a representative of all the days? Does this account for seasonality? There's a lot of unknowns here, and really the idea here is that how can we provide more continuous data in order to be able to update these signal timings on a more regular basis. Of course, the ideal state that someone would talk about is that, okay, let's have adaptive everywhere or everything's automatically controlled. Well, the reality of the world is different from that, right? It's more about how can you improve the current status of signal timing rather than sort of, again, completely revolutionizing the space, because it's about agency adoption as well too. It's not just about the methods, it's about the fact that an agency has to adopt that new method. So again, it's collected on a specific hour. So the new approach of AT-SPMs, you might have heard of them, automated traffic signal performance measures. And the idea is that let's measure the ultimate performance and let's do performance-based optimization as opposed to sort of the traditional model of demand-based. So in the traditional model, you sort of capture the demand, you make some assumptions regarding capacity and other metrics, and then you measure performance. But with this way, you can measure performance directly. And then the performance doesn't need to be necessarily limited to vehicles, right? You can measure the performance of cyclists, measure the performance of pedestrians, measure performance in terms of equality. Even for vehicles, what does average delay mean for a driver, right? A number of stops makes more sense for a driver than average delay. We're trying to minimize average delay, but what does that mean? Is that a good experience for the driver when they're going down a corridor, for example, and they're hitting multiple red lights, even though the average delay might be minimized, but that's not the experience that the driver is looking for. So or cases where there might be multiple split failures in order for a queue to clear. From a sort of a numerical perspective, that might be the minimal delay, but what does that mean in terms of the experience of a driver waiting multiple cycles in order to pass through, or a pedestrian or a cyclist? Doesn't matter really. So it's more about measuring performance than it is about measuring the demand. So basically, if we want to sort of simplify a little bit, let's say a signal is timed every 3 years, and this is what usually what happens is that delay, or let's say performance is a better name for this, starts to deteriorate due to changes in travel patterns, all sorts of different types of changes that happen, maybe new developments. And that typical retiming is that case, but with ATS, because the idea is to let's keep the performance nice and healthy on more smaller increments, as opposed to allowing things to get really bad before we sort of start to look at it. So it's about continuous measurement of performance. It's less about measuring demand, more about measuring performance. And then even for modeling purposes, the data, because the high-res data is being collected, it helps with calibrating models as well too. So if you're creating a model and a simulation model, all of this high-resolution information that's coming from the controller, and I'll explain a little bit what they are. That's basically that could be used to calibrate the model as well too. So having better representation of what's really happening out there. So you might be asking, okay, where does this data come from? It's really a combination of different types of sources that are available, that are mostly available at an intersection. So the first one is the traffic controller. So traffic controller, especially the newer generation ones, they actually log the high resolution information. So they're actually logging that I gapped out, I maxed out, or this is the amount of green that I gave to this phase, or this is the amount of red that I gave to that phase. So all of that information is being logged. There's also detection available at the intersection, right? So there's all sorts of different detection available at a lot of intersections, and they're mainly used for actuation purposes. But there's also the opportunity here to be able to combine these data sources together, right? So you can imagine a stop bar detector that is heavily occupied during green time and during the red time. That's a pretty good indication that, you know what, it seems like this movement is near saturated or saturated. Or arrival of a vehicle on an advanced detector as the light is green is an indication of an arrival on green, for example, or arrival on red the other way around. So there's a lot of, I don't want to get into the details, there's a lot of information available online in terms of what the metrics are, but this is the general idea, is that you sort of tap into the controller, tap into the cabinet, into the at the intersection, and you try to bring all this data out, and by coming up with clever ways to be able to generate performance measures. Another one is travel time data. So our SmartLink device provides that information through MAC address sniffing. So there's a bunch of performance measures, as you can see here. All that information that I talked about, we take that, generate a number of performance measures that actually show what the controller is doing, what are the volumes that are happening, delays. In terms of performance, we have split trends. We're actually showing the level of saturation on different movements, and through computer vision, there's turning movement counts, and a bunch of safety performance measures as well too. So this is the interesting part. Again, computer vision really opens up the opportunity here, and I really feel like this is just the start of it. So because we have computer vision available at the intersection, we're classifying, detecting, tracking vehicles. We have the signal light status. So all of these dots that you can see as a vehicle at the middle of an intersection overlaid with the signal status. So this is a vehicle, for example, this up here. After 6 seconds after the start of the yellow interval, it's passing through the intersection, right? So this provides an insight into the actual sort of red light runner. And when you start to sort of gather this information at a large scale, you can start to identify where the hotspots are and where the problematic movement or intersections are. Another one that really computer vision enables that we have available, again, this is just the start of it, is pedestrian compliance. So detecting pedestrians, capturing them, tracking them through an intersection. And we also have the pedestrian signal status as well too. So we can actually detect the number of pedestrians that are compliant, non-compliant at an intersection. And again, at a large scale, being able to identify the hotspots that the most non-compliance is happening. Usually non-compliance doesn't automatically mean a safety issue, but it is something to investigate. All of these dots actually have a timestamp associated with them, and the user can actually go back to the video and see, okay, what was the context around this? Why did this happen? And be able to address that. Usually the cases are that cycle lengths are too long for that specific time of the day, and people are just taking chances, right? Wanted to share a bit of interesting thing that we've been working on in the past few weeks, past couple of months, sorry. And the motivation around it was that, as you can see, there's a lot of data, right? And public agencies don't have the resources required in order to be able to actually manage this data. So even if you're presenting them in nice charts and everything, there's just not enough resources available for them to sort of go and dig into that data to find a problem, find a traffic issue or an efficiency, which is completely fair. And maybe that's possible on 3 intersections, but what about 30? What about 300 intersections? So in order to address this concern about too much data, what we did was that, and this is coming out in a couple of weeks, which we're very excited about, is we've created an engine, a smart engine that actually crunches all of that data that's being captured that I talked about, and it actually identifies inefficiencies automatically. So you can imagine that a city like this, with a number of intersections, and we're actually identifying which one of them have suboptimal green splits, for example. So it's not just a simple threshold-based approach. We're actually identifying where there's some kind of inefficiency happening. And this is just the start of it, to be honest. Right now we're targeting sort of suboptimal green split or progression issues throughout the corridors that are important to the user to have progression. But any kind of problem can be added to this, right? Imagine a data source like even transit comes into play, and we define what a bad performance in terms of transit looks like, or what a good performance looks like, and that's just sort of an added layer to this. So we've created the foundation and sort of be able to automatically take that data and really be able to convert that into insight as opposed to being raw data. And again, in a case like this, I click on an intersection, it'll take me to a page where I can exactly see which movements are the movements that are suffering, and how does it compare with the competing movement, and is there an opportunity to be able to improve the situation here. So really makes it easy for public agencies that previously may not even had cabinet connectivity, so I don't even know whether the lights are working or not, to a situation where now they can actually see which movements are occurring and how they need to change the timing. It's a massive shift. I think I have a bit of time here. I'll just quickly go through a sort of a case study here. How much time do I have? Sorry.
10 more minutes, maybe around 10 minutes.
10 minutes before the question. Okay, sure.
Yeah.
Okay, I think that works. Thank you. I just want to provide sort of an example. This is an interesting example of how the data helped an agency be able to diagnose an issue, identify the issue, diagnose and produce a solution, and be able to measure the impact of that and improve the situation. So this is an intersection with an LRT passing through. So the light rail transit vehicles are passing through in these two rails. One goes northbound, one goes southbound. And at this T intersection, we were installed, and there were some complaints coming in terms of the operation. So this sort of provides you with an insight of what type of data is being captured, and at the same time sort of tells the story of what happened here. So these trains get priority, and in order to get priority, they use preamps in order to do that. And one of the data that again goes through the controller, and controller really determines that logic, are preamps, and we're reading that. So throughout the day, you can see all of these different bars that you can see. This is the duration of the preempt that's happening. So the train requested a preempt, and this is the duration that the preempt was in play. Sometimes what happens in the field is that these preempts get stuck, so the preempt does not go off. And in cases like this, if it goes beyond like 600 seconds, we actually send a text message to the technician, and they are alerted on the fact that the preempt is stuck here, and they will go and fix it. But apart from sort of the operational side, it's interesting from data perspective of how often the trains are actually interrupting the timing plans. So we wanted to look into, so the agency was interested in looking into and see, okay, what's going on with our timing plan now that there's so many interruptions happening, and probably to our timing plan, like how is that impacting operations? So this is a pretty good picture of like the before and after in terms of timing. So the picture that you can see on the screen, the top picture is a what's called a phase interval graph, basically showing the amount of red, green, and yellow that's being allocated to this movement. You can see there's a very constant cycle lengths that are happening because this intersection was coordinated with the subsequent intersections along the corridor. And as you can see in the bottom graph, so after the operation of the trains, you can see that the controller is barely able to keep the cycle length constant anymore. So you can see the significant amount of variation that's happening in the cycles means that the offsets don't even make sense anymore, right, between the intersections, because the prerequisite to coordinated systems is a constant cycle length among them. So basically, in a case like this, because of the interruptions that are happening to the actual timing plan, the controller is trying to go into coordination again, and then it gets a preempt again. So in a case like this, when this is happening, the agency can clearly see this and decide that, you know what, maybe coordination doesn't even make sense anymore here. Maybe we'll focus on sort of more locally on pedestrians and cyclists, making sure that more equality is provided between different movements, because there's really no point in keeping this this corridor in coordination where it's sort of struggling to get back into coordination, but it can't. Another issue here that was interesting, it really goes back to sort of the power of that data provides. So after the operation of the LRT vehicles, one of these left turns. So one of the graphs that actually provides some insights is the delay graph. So it's actually showing us the amount of delay that each of the movements are experiencing. Before the operation of the LRT, that left turn, the northbound left turn, had the sort of the bottom line, and then after the operation, had the top line in terms of delay. So you can see 5-minute delays were around 150 seconds. So that's around like 3 minutes of waiting. So they wanted to investigate, so what's going on here, why the delay is so high, and what they've really figured out was that this movement is being neglected due to the preempts that are happening. So just as this movement is going to be serviced, a train arrives, it gets neglected, and then it doesn't go back to this movement again. So the agents are able to find this, and what they did was that they actually enabled that left turn to have a reservice. I don't know if you've heard of reservices or not, but it's reservicing the same phase before sort of going into the entire cycle. And as you can see here, you can sort of see those smaller cycle lengths that are happening. Those are the cases where the shorter cycle lengths, those are the cases where the reservice is happening. And they put this solution in place, but they needed to know whether this is working well or not. So they use this, one of the other graphs that we have. So the graph that you can see on the screen, this is more of a performance graph. So it's actually showing the level of saturation that's happening on a movement. In this case, red is bad because it's causing split failures. So as you can see, like before and after, the amount of red that you can see or the poor performance have reduced significantly here. So they were able to not only diagnose the problem, put in a solution, and then be able to measure the impact that this had. And then we have sort of the software to be able to exactly quantify how much that is for reporting purposes. So in this case, it was a 25% reduction. Another one that was quite interesting is pedestrian compliance. So the data was showing quite a bit of non-compliance during the preempts, and this was at another intersection. So overall, it was 12% non-compliance from the pedestrian side, but 50% of that was happening during preempts of when the trains were arriving. So it's kind of interesting to look into it and see why is such a significant number of non-compliance happening during that time. I'm just going to show this video here, which would shed some light on what was going on. So as you can see, this is a train. So the train tracks on the top left corner of the screen. That's where the train tracks go, and then further down is the train station. So as you can see, during the preempt, when the train is arriving, it has nothing to do with this movement. The gates go down for the other movement, but this movement actually should not get a red, so no one should be stopping here. So as you can see, that pedestrian that was passing through, that was actually a non-compliant pedestrian that was passed. So vehicles are stopping here, but it's odd. Why are they stopping for just like 5 seconds? Pedestrian thinks that it's okay to pass through. They pass through. The other one thinks, okay, I'm going to pass through as well too. It seems to be red, but it's actually green. So sort of creates an unsafe situation. Most of the cases of the non-compliance was actually happening during this time. So it was interesting to sort of go into the data and see why are these vehicles stopping? They're not supposed to stop during these preempts. And then what we saw from the data was that, yeah, there's actually these 5-minute blips of short 5-second red times that are 4-second red times that were happening and causing this situation. Every day that was happening multiple times and creating an unsafe situation for pedestrians. So ultimately, the agency they went in is actually an issue with the preempt that was triggering the signal as well too. So again, the power of data to be able to really identify this thing and being able to address an issue that could have turned into a serious safety issue. I want to take like a few minutes just to talk about sort of my perspective of like the future of traffic and transportation engineering in this space and sort of where sort of the next generation of traffic engineers in this space would sort of look like. There's no one really knows what the future holds, but based on the current evidence, it's very obvious that it's going to be increasingly data focused and data driven. Absolutely, there's a massive amount of data being available. The question that really becomes is that it's not about managing the data and that sort of thing is one thing, but what's really important is that what do you do with that data? And that's the question that a lot of these agencies have, a lot of tech companies have, even consulting companies. What do you do with that data, right? You're capturing the data, but how do you turn that into an actual impact? That's the bigger question. It's becoming more and more technology centric, absolutely. Again, there's right now there's pretty much a web application for any type of transportation application, transit, traffic. Everything's becoming more connected. So definitely more technology centric. It's the center of smart city initiative. So something interesting. So if you want to sort of pay attention next time, any type of agency, like a lot of companies, even though they might not be in the transportation space, in order to get into the smart city space, which is a massive opportunity in the next sort of 10, 20 years, the angle that they take towards it, it starts from transportation. So very rarely you see that, let's say TELUS, for example, they're providing sort of a telecommunication, and they've sort of entered the space of smart cities through transportation, right? There are new careers becoming available. So smart city sort of analysts or directors or that sort of thing, that they are becoming more and more available, even in the technology world. So maybe 5 years ago, a career path for a person in traffic world was like, I go into consulting and sort of stay there. But right now, there's a lot of paths. There's a lot of companies that are taking the path of sort of making things smarter, or the technology companies that are working in the space of transportation, and they need people with domain knowledge. It's becoming more and more automated, increasingly complex. So complex problems problems are becoming more and more complex. And there's a lot more demand management happening as opposed to capacity management. So the industry is mainly used to sort of everything is given, and I'm going to manage capacity. But I think there's a lot of opportunity to be able to now manage demand as opposed to just managing capacity or managing them together, pretty much. So there's a lot of changes happening, but how can you prepare? I think there's two areas, both hard skills and soft skills. I think both are extremely important. It's extremely important in this space to specialize in something, right? So if you're in the transit world, specialize very much in that, but understand the others. If you're in the traffic world, specialize in it. If you're good at simulation or you're good at signal timings and that sort of thing, specialize in it, or in the ITS space, but understand the rest. That's extremely important. Domain knowledge, really take advantage of the professors that you have access to at the University of Toronto. It's a massive opportunity. Really get a good grasp of the domain knowledge. That's where a lot of companies are lacking, right? So if you go entering a technology company, you might see that they have maybe hundreds of even data scientists, but no one really has the domain knowledge in order to be able to take that data and really make it and convert it into impact, because without strong domain knowledge, that can't happen. Be tech savvy, understand technology, understand cloud computing, learn to code. That's super important. I understand this is a graduate program, so I'm sure everyone's sort of comfortable with that. Get more comfortable with data. Again, everything's going to be more data driven. Try to understand the data. Don't just blindly use the data. Just visualize it simply. See what you can get out of it. Nothing really beats a good thought into sort of a visualization and looking into and seeing what can you understand from it. It's not always about fancy machine learning methods. It's about sometimes just visualizing the data in a very simple way and just looking at it, right, and trying to make sense out of it. For softer skill sides, as important, definitely. In this space, I think it's really important to be able to tell a story, right? When you have data and you want to turn it into impact, and you want to, even if you're, I will for sure. I'll wrap up in just a minute here. I think it's important to have the storytelling capabilities. Having good presentations, that's definitely a great skill to have in writing. Become business savvy. So don't just focus on a specific area. Understand businesses. How do private businesses run? What kind of metrics do they follow? What are the sort of hierarchies that they have? It's good to know these things. Again, I don't think it's necessary to go into details. Understand financials. Again, if you really want to get into sort of the space and really show yourself, I think it's important to understand the financial sides as well too. Keep yourself up to date with the industry, whether it's through magazines, I don't know, ITE journals, that sort of thing. Keep yourself up to date. That's super important, not just from a research perspective, but really what's out there, right? From a technology perspective, different companies out there, what are they doing? Because usually the technology or the companies or the vendors that are out there, they're way behind of research, right? So they're more closer to reality. And understand real industry problems. So ask yourself, like, is this really a problem in the industry? And talk to the people in order to understand them. Thanks a lot for listening. I know I babbled a lot here, and hopefully, if there are any questions, happy to answer. If anyone has any thoughts they want to share, go ahead.
Yeah, so we have one question from Professor Bahar. You can go and unmute yourself, Professor.
I think unmuted. Hello?
Hello, we can hear you.
We can hear you, but it's a bit unstable.
Okay, my question is about the detection range at intersections. Like some of our adaptive traffic signal control research requires that we see approaching traffic from as far as like 200-300 meters. We want to see individual vehicles, track them, measure their position and speed as they approach the intersection. Is Myovision working on a product like this? Because from your presentation, it seems that your technology and applications are much closer to the stop bar and within the intersection, but not looking far from the intersection.
The great question. Yeah. So it's just a matter of camera. So we don't currently have that product, but basically we've seen sort of with closer by intersections, they've used sort of the upstream intersections video as sort of an upstream detector for a downstream intersection if they're sort of close by. But we currently don't have that product, but it's just a matter of sort of applying the same algorithms onto a upstream sort of detector, similar to like a bullet cam, for example.
Mainly, I'm talking about like if this is. I'm not sure if you see my screen.
Yeah, I can see it.
I want to see these 300 meters.
Right, like the entire sort of length of it, right?
Yeah, so I want to detect and track individual vehicles to give me position and speed.
Right. 300. So this really depends on the positioning of the camera. So I think something like that would be possible if you put the camera right at the 150 meter in between, because it could go sort of 150 on either sides. So that is possible, but the camera needs to be installed midway, and there's a lot of issues with that as well too. So right now with our current offering, I could think about something like that in order to be able to do that. But something that's happening probably in the future is sort of having the more direct cam that's looking at an approach, and then you probably would be able to get. Not sure if we can go up to 300 meters or not. That may require a couple of cameras to be able to do that, but yeah, that's all I can sort of think of at this point.
Okay, all right, thank you.
Yeah, no problem. Any other questions or thoughts?
We have one question. Just let me give them permission.
Junshi, you can now unmute yourself.
Yeah, thank you. I have a question also related. So, does the Myovision product do vehicle tracking across multiple cameras so that it can recognize the same vehicle passing a series of intersections or across several cameras?
So yes and no. So the yes would be sometimes when intersections are very large, we require sort of two 360 cameras, and between those 360 cameras, we actually do track sort of among the two cameras. But doing that sort of between different intersections, no, we don't do that, and that sort of creates a lot of privacy issues as well too. If you're sort of tracking the vehicle throughout multiple intersections, but at one intersection, yeah, if it's large enough, sort of one camera detects it halfway through, and the other camera sort of picks it up halfway in order to be able to exactly detect where they're sort of the turning movement that they're making.
Thank you.
Yeah, no problem.
So we have one question on the chat box. Are working cameras provided, as there are many advanced cameras with the edge processing and analytics?
Yeah, that's another thing, right? Like there are cameras. They need to have. There's lots of cameras out there. They need to have edge processing capabilities in order for like sort of the algorithms to run on. But also their processing power matters as well too. There's a lot of factors here, right? What is the resolution of the camera? What is the processing power of those edge processors? What are the sort of the communication methods? There's sort of a lot of details, and can the algorithms be applied to that? Absolutely. But is it an easy job to be able to sort of integrate with all sorts of different cameras? Well, that's a different story. But that's if that sort of answers your question.
Okay. Thank you so much, Sajad, for your presentation. It was very, very interesting. And I think we reached the limit of the time. So thank you all for joining us, and have a nice day.
Okay, thanks a lot.
Thank you.
Bye-bye.
Bye.